All right, hello folks. We're going to do a pretty short and, to be blunt up front, ad-libbed video to give you a little bit of additional information on what we talk about when we're discussing radar and reflectivity and velocity and things like that. So this is designed to go with Professor Gobert's short write-up or video on using radar data within the Python interface. And so you've seen a little bit about radar. You've no doubt looked at some stuff with radar. And so this is not designed to be all encompassing, but more or less an 8 to 10 minute snippet that may get you back engaged within this, especially as we're working our way here into the heart of severe weather season. And so when we talk about radar data, we're simply talking about these waves that are being transmitted by our Doppler radars, and then we are effectively listening for a response. And so although the schematic here for a standard Doppler radar suggests that the transmit and receive are about equal, in reality the time spent listening for a response is substantially greater than the actual transmitting of the signal. In fact, I think the data suggests that for about every hour a radar is running, it is transmitting a signal for about 7 seconds and listening for the remaining 59 plus minutes of that time. So here's a standard radar transmitting a horizontal pulse and then receiving back. And it's going to receive back from whatever it hits. It might be a severe thunderstorm with a lot of hail and rain. It may be a flock of birds. It may be something on the order of ducting due to an inversion of the atmosphere, which actually can cause the waves to bend and actually kick into the ground. You may hear terms down the road such as anomalous propagation. There's tons of lingo when it comes to radar, and I definitely encourage you later in your undergraduate career to take our course in radar meteorology with Professor Wolf if you find this interesting. But what we'll look at today is, again, the difference between radar and then this idea of dual polarization Doppler radar. And so our radar here on campus is a dual pole radar. In fact, we had a dual pole radar here at Valparaiso University long before the National Weather Service locations were receiving dual pole, and it was the source of a very interesting grant that we had about 10 to 12 years ago, where we were launching weather balloons regularly to learn a little bit about what capacity dual pole radar had to learn about icing and other phenomena within some winter storms. And so the big difference is here we're transmitting both in the horizontal as well as the vertical, which is designed to give us a three-dimensional look at what is in the sky, what we often refer to as hydrometeors. Are they circular? Are they flat like hamburger buns? Are they needle-like structures? And so we can learn a lot about whether it is rain, snow, or something else that is falling through the atmosphere. And so without further ado, let's take a look at a little bit of radar data. And so this is being done on Sunday, April 19th. And so if you've been paying attention to the weather, you may be privy to the fact that there is a moderate risk out for much of the south and southeastern United States. Basically an area here from Louisiana across southern and central Mississippi, southern and central Alabama, and into Georgia, with a much lesser risk further north here as there are much cooler air and not necessarily getting the same thermodynamic parameters. This idea of both temperature and moisture being a critical role, and you'll learn a lot more about what goes into severe weather in Bet 279 should you choose to take that elective. And so what we're going to focus on right now is what exactly are we looking at? The idea that you have a number of different radars, and this is a composite putting together basically a mosaic of all little tiles from different radar offices. And so you see a lot of kind of dull colors, blues and light greens. These are going to signify where the reflectivity is low. It is being received and transmitted back to the radar, but it's not necessarily transmitting a large percentage of the energy back because it may be light rainfall. It may even be rainfall that's not fully reaching the ground. You can also see, especially here across areas of Mississippi and into Alabama, some bright, deep yellows and reds. And this is going to be areas where our radar beam, which is effectively sent at a number of different elevations, ranging from about a ½ degree above the horizontal, all the way up to about 19½ degrees, depending on the scan strategy. And so here, if it's hitting a portion of the storm high up where there's large hail, it's going to reflect a very large percentage of that energy back to our radar. And so we can tell a little bit about what's going on in terms of intensity of precipitation within a cell. And so let's go ahead and let's zoom in here to the Jackson, Mississippi. Here I'm looking on the College of DuPage website. And so we can look again at this reflectivity. And you can notice here where I'm trying to circle my mouse where the radar location would be just outside of Jacksonville. And so if we go ahead and we loop this, we can see, if I scroll down, the general motion of your storms. It looks like the city of Jackson is getting hit quite hard by some of these heavier precipitation echoes. You can see a couple other cells here that are forming and sort of joining in with the line. In fairness, College of DuPage does a number of things very well. Their radar is not necessarily going to be the smoothest that you look at. Again, I'm guessing a number of you have looked at Radar Scope or a number of other applications to be able to view radar data, but this will get the point across. And so again, out here maybe across areas of Arkansas, not real heavy precip, areas here just some probably constant precipitation here across northern Mississippi, and then these are going to be your intense thunderstorms. But there's a number of other things that we can look at when we deal with looking at radar. And so this would have been a base reflectivity. You can see some of these tilts that I talked about, a ½ degree being closest to the ground, and then working our way up through a number of different tilts. Another phenomenon here is known as base velocity. And so the key thing that we can look at here in velocity is the fact that we have a lot of greens and reds. Greens are winds that are inbound toward the radar. And again, our radar here is located a little bit to the east of Jackson. And so all of this area here, when the radar signal is being received back at the radar, is suggesting that the energy is moving towards the radar. Anything that is reflecting off of has some type of component of wind towards the radar. Red is outbound. Green inbound, red outbound, or gyro. Kind of a fun way to think of it, even though it's not spelled like the delicious treats across Lincoln Way at King Gyros. But at the same point, we're looking at not a lot of interesting phenomenon other than maybe some brighter greens here, suggesting some stronger winds. And there is a very difficult thing to fully grasp at this point, effect that it's only looking at what's coming in directly towards the radar. We know that if we look back, that not everything was blowing either directly in towards this little black dot or directly away from that little black dot. And so we're just looking at that perpendicular component. There's a number of other products here. Storm relative mean velocity. Here we're simply trying to take out that storm component and look at what the winds are like within the vicinity of potentially a supercell thunderstorm to try to determine whether or not there's a couplet or any type of localized rotation within a thunderstorm. Differential reflectivity and correlation coefficient are looking at some of the phenomenon related to our dual polarization Doppler radar. When we look at things such as these along with KDP or specific differential phase, hydrometeor classification, the thing that I can probably translate to you quickly today is that if you've ever seen like tornado debris signatures, or what's oftentimes thrown around in slang as a debris ball, we're looking at the fact that because we're looking at both the horizontal as well as the vertical transmission, we can pick up things that are, well, much larger than raindrops or hailstones, things that might be debris from homes or trees or things like that. And so we oftentimes get very localized, intense signals that are going to be part of these dual polarization products. Another thing that you may note, and even though it's not showing up here, we get base reflectivity, but if you're on a National Weather Service website, you'll notice often that it shows base reflectivity or composite reflectivity. The big difference here, in fact, let's give it a try, even though I don't have it set up, which hopefully means it's not a complete disaster. Let's make this a little smaller. All right, let's go down to the National Weather Service radar here. You'll notice that it shows up as base reflectivity. We can see some real heavy area where it's been raining heavy for a while, flash flood warnings that would be in effect. But you'll notice here that we have base reflectivity and also composite reflectivity. When you see composite reflectivity, this is that idea that it's looking at a number of different tilts, and it's simply showing you the tilt that shows the greatest reflectivity. And so if you compare base and composite, you'll notice that the composite is always the same, if not greater, at each location, because it's picking out that level at which the reflectivity is highest. And this can be quite valuable within some situations. And so we'll end this little bit here by looking at a supercell from last year across portions of Texas. And so here you can see in this example we have a pretty nice hook echo. And so what we're looking at on the left is a super res reflectivity. This is from the Radar Scope Pro software suite. And so an elevation of a 1/2 degree, and it's seeing very intense areas here on the north side of our supercell, kind of an interesting north-northeast motion. These are going to be this is going to be where you see your heaviest precipitation, your hail, and then you see this little bend on the backside, our hook echo. And so you can trace on the left here our super resolution velocity tilt. And so you'll notice here where we have areas that we're tracing where that green and red, when those green and red values match up very close to one another, that's suggesting a mesocyclone, a rotation within your thunderstorm, which we may expect to find right in that apex of or right in the area there with your hook echo between what's known as your forward flank downdraft and your rear flank downdraft. And so radar can be a critical key to help determine whether or not a storm may present the risk of a tornado, either A, before a tornado actually were to form, or B, in areas that there might not be anyone able to see a tornado and help to get a warning out more quickly. And so this will be the difference when you look at a tornado warning in which the tornado has been indicated by radar. This is the type of signal that they're looking at in conjunction with things such as tornado debris signatures, which are going to likely be seen more commonly when you are dealing with a large town or city where things are actually going to be lifted up into the air by some type of a tornado or strong wind signature. That's your very brief, approximately 11.5-minute discussion on radar. I hope this has gotten you excited to look at a few more products, and I encourage you to take some time later this spring or into the summer and just glance at some radar data. It's going to make you better prepared for your sophomore level courses, and especially if you're ready to go out to the dusty plains of the United States next summer in one of our convective field studies. So I hope you've enjoyed this video, the last one I plan to make for the semester. Take care, and we'll talk to you all again soon.